This is part two of the screencast that accompanies my PowerPoint presentation on general relativity. Once again, however, make sure that you watch my actual lectures on general relativity prior to watching these screencasts, as I only cover the material here rather quickly. Okay, now after black holes, existing as a solution to the Einstein field equation is another type of geometrical construction that's called a wormhole. A wormhole is basically a four-dimensional tunnel, if you will, through space-time. This picture right here describes the basic geometry associated with a wormhole. You have two openings, if you will, in space-time, here and here, that are referred to as the wormhole mouths, and then connecting the two as a tunnel through hyperspace is what is referred to as the throat. As of now, wormholes have never been observed in nature. Right now, it only exists as a solution to the Einstein field equation. Basically, right now, it's just math. However, there are some fantastic possibilities associated with such construction. First of all, wormholes might be able to be used to travel extremely vast distances more or less instantaneously as a tunnel through space-time. What we have right here on this slide is right here a two-dimensional sheet, if you will, that depicts three-dimensional space, and then in a fourth spatial dimension connecting two points on that sheet are the two wormhole mouths. Let's say that we have a star right here and another star right here. Through normal three-dimensional space, the distance between those stars may be quite vast, say thousands of light years. However, as by means of this tunnel through space-time, the distance from one wormhole mouth to the other may actually be very small, like just say a couple of centimeters. So then therefore you would more or less be able to instantaneously travel from one side of the wormhole to the other as a four-dimensional tunnel through space-time. One of the interesting things about general relativity that we've found over the years is that the theory will make some wild mathematical predictions. Initially, nobody will believe those predictions, but then we find examples of phenomena that cannot be explained any other way. Black holes are the prime example of this. Okay, now this right here is a still photograph from the film Interstellar. Interstellar makes some mistakes with respect to general relativity, but it also actually gets a lot of things right. One of the things that it does get right is that if you were in a spaceship approaching the wormhole mouth, you would actually see it as a sphere. And the reason why is because you're basically looking at a four-dimensional object in normal three-dimensional space. Once again, the allegorical story of Flatland allows us to visualize a fourth spatial dimension, even though we only see three-dimensional space around us. As I described quite extensively in lecture, general relativity suggests that a wormhole could actually be constructed as a time machine to the past. There are some restrictions, however. It would only be useful to go back to a point in time after the actual construction of the wormhole. So because of this, time travel to the past without a wormhole is probably impossible. The idea, however, has actually been tested. It was tested very famously back in 2009 by the British physicist Stephen Hawking. Stephen Hawking has since passed away, but Stephen Hawking was one of the world's experts on general relativity, and he tested the idea of trying time travel to the past without a wormhole. Here's how he did it. What he did was he threw a party. And at this party, he had it catered. There was all this food. There were all these drinks and so on. And then basically he sat in the middle of the banquet hall or whatever it was, the reception hall that they used for the party, and he waited for the guests to arrive. Nobody showed up at the party. After the party, however, that's when Hawking sent out the invitations. He sent out the invitations to the world's governments and the world's universities, basically to time travelers in the future, welcoming them to the party. In other words, why don't you come back to the past and visit me at my party, and we'll have a grand old time. Nobody showed up at the party, therefore time travel to the past, at least without a wormhole, probably impossible. However, here's something rather interesting to ponder. In 2016, the Chicago Cubs won the World Series. Now, back in 1993, at a high school in Mission Viejo, here in Southern California in Orange County, this high school student named Michael made a startling prediction in his yearbook, and he made this prediction in 1993. He accurately predicted that the Cubs would win the 2016 World Series. As you can see here in the yearbook photograph, you heard it here first. Okay, this picture has been confirmed with multiple examples of the yearbook from this high school back in 1993. The interesting thing, however, about this person, Michael, is that he has not been seen since. So then, therefore, it's been hypothesized that Michael perhaps is some sort of post singularity, time traveling artificial intelligence, traveling back in time and masquerading as a Cub fan. Now, whether or not there are actually any time traveling AI out there masquerading as Cub fans is an open question. But here are a few other interesting coincidences about 2016 to consider, besides the Cubs winning the World Series. Back in 2016, the Large Hadron Collider, that's when it actually started to operate at its full strength. In other words, it was doing particle physics collisions at the highest energies possible based upon the design of the machine. Is that a coincidence? Something else that's interesting to ponder as well, perhaps as a coincidence, is that somewhat unexpectedly, Donald Trump was elected president in 2016. Okay, and then applying general relativity to the universe as a whole. When you apply general relativity to the universe as a whole, it suggests that the universe as a whole has a finite geometry associated with this. I described this extensively in my lecture, but right here is a depiction of the old video game Asteroid. As I described in the lecture, the game Asteroids appears to be an infinite two-dimensional universe while you're in the game, but because the sides of the screen, top and bottom, and the right and the left are connected to each other, the game of Asteroids actually takes place on the surface of a three-dimensional universe that is shaped as a torus. General relativity suggests that our entire universe may actually be some four-dimensional version of a torus, what's referred to as a hypertorus. General relativity also predicts that the universe expands, and it expands without a center. That was confirmed back in the 1920s observationally with powerful telescopes. Once again, general relativity makes some wild predictions about nature. We initially tend not to believe those predictions, but then we see phenomena in the universe that can't be explained any other way. Okay? All right, so that concludes this screencast. As I said, do make sure that you watch the lectures prior to observing the screencast.